So I would like to extend a very warm welcome to everyone who has joined our machine learning seminar today and also throughout the year for our 2024 seminar. Unfortunately, we've reached the end of our seminar, but we have a fantastic guest today, so I'm delighted to introduce our speaker. Before I do that, just a few housekeeping topics. This meeting is being recorded for those of you who are new to the seminar series. In order to access the recordings, they will be put up after the seminar series on the USC YouTube page. So you just need to search for Universitätsspital Zurich on our YouTube page, and then you can find the machine learning seminar playlist. In addition, if you would like an SGR SSR credit, please drop your email in the chat and we will send those through to you afterwards. And finally, if you have questions throughout the presentation, please don't hesitate to drop those in the chat as well, and we will get to them at the end. So on that note, I'm delighted to introduce our speaker today, Prof. Thomas Küssner. He is based at the University Hospital of Tübingen, where he is the chair of the Medical Imaging and Data Analysis Lab. He received his PhD from the University of Stuttgart in 2017 and subsequently worked in the School of Biomedical Engineering and Imaging Sciences at King's College London. Prof. Küssner has vast experience in the field of AI and MRI with hundreds of publications, and he also currently serves as the editor of both the Magnetic Resonance Materials in Physics, Biology and Medicine journal, as well as the Applied Magnetic Resonance journal. Furthermore, he is in the governing committee of the ISMRM Motion Detection and Correction Study Group and currently chairs the ISMRM Motion Workshop. So his research group is working on artificial intelligence-enabled multiparametric and multimodality medical imaging methods, and his particular focus is on MR-based motion imaging correction and reconstruction, as well as the advents and advancements of AI in MRI. So on that note, we are absolutely delighted to welcome Prof. Küssner to discuss the topic of integration of AI into the MR workflow. And I will hand over to you, Prof. Küssner.
All right, thanks a lot for a kind introduction and thanks for having me here. I will share my slides and want to talk you through today a little bit about the integration of AI into the MR workflow with a little bit of a provocative title, are we there yet? And in order to understand that or to answer that question, let me guide you through a little bit about what it actually means by the MR workflow and what kind of integration we can achieve. So if we think about the whole workflow, this really starts for us from the very, very beginning. So we need to think about the patient presenting itself to our facility or to some outside facility and then referred to our hospital. We need to schedule an imaging session for the patient, any other diagnostics that are required. But then the main and nitty-gritty part is then the actual acquisition, the processing of the data, the perception of the data, and then the final reasoning. Once we have done that, we also need to report, or our clinical colleagues are reporting what was diagnosed and communicating this then to the referring physicians and also to the patient. So I want to talk today or want to zoom in a little bit more just about this part from the acquisition to the reasoning process, because there so far has been the most developments in terms of AI into this workflow. So just a zoomed in picture here, what this means for the MRI world is we can perform the acquisition, then we have our raw data. Now we need to process the raw data. Depending on the acquisition scheme, we get different images of anatomical, quantitative imaging, some functional imaging. And from these images, we can then do further downstream tasks like motion correction, lesion detection, quality control, segmentation, biomarker extraction, which at one point can be then hopefully helpful to decide the diagnosis, estimate survival rate, or decide for follow-up treatments. And what we have seen in the recent years is that AI has been integrated into these individual steps, sometimes targeting one specific aspect, sometimes targeting several different processing steps. So I want to guide you through now these different processes and look first into the acquisition side, what has been proposed here. This is slides I got from Wendy Strucknell, and this is also information. Oh, sorry, video is not playing back. of our of an automated assisted view planning. So when we are setting up a protocol or have a certain indication for a patient, we always have this huge comprehensive MRI protocol in our background. We decide based on the initial diagnosis and the question at hand, which protocol we should be running. And now we have AI-assisted tools that help us in planning, that help us in estimating, for example, inversion times automatically. So this all comes down to a really one-stop shop solution where you just need to press one button click and the rest is automatically filled in and planned for you. But we need to be prepared for any irregularities that are happening during this acquisition. So, for example, changes in the respiratory or cardiac cycle that will change then all your triggering, all the amount of phases that you can acquire for this example. And then here on the left-hand side, you should have seen a video where we, like in real time, switch them between these different protocols. But you can go down onto this website and check it out there. We also have there further information material because we went into more length how this can be done in 3 member-initiated tutorials that were run at ISMRM over the last 3 years. Another way on how we are working on the acquisition side, and the slides I got from my previous colleague Olivier Chaubert, who is now at UCL. He looks here at real-time phase contrast MRI to monitor the cardiac output during rest and stress perfusion. So what he needs is a real-time reconstruction. So this is this network here on top doing. And from there, he wants to segment then the left ventricle to estimate then with the segmentation network to estimate then from there the beat-to-beat first heart rate and then the stroke volumes and the respective cardiac outputs and flows that are measuring coming here through. And this can be done real-time live on the scanner, allowing us then actual interaction. And this we can develop further and with integrate with any other means. So we see this is not just a reconstruction, but combining then already a reconstruction with some downstream tasks. And that's what we will also see more in this further steps. But an important ingredient for it is still the reconstruction that we need to run because we just have the raw data in K-space in the Fourier domain, and we need to come to an image to draw any conclusions. We have also seen here that the deep learning helped us a lot in developing this field. And there are different ways on how you could look at the machine learning for image reconstruction. You can first do an image enhancement network where you start with your undersampled case-based data, have a regular joint operator that maps you back to the image domain, including coil sensitivities. And then you learn a network that goes from this aliased and noisy image to a nice high-resolutional de-aliased image. You could also do this in a physics-based unrolled way. So now you have a neural network that learns iteratively over several consecutive steps how to update this information, and furthermore includes then a data fidelity term that ensures consistency of the reconstructed samples to the acquired samples. Or you could formulate this problem completely in the case-based domain. So you're going from an undersampled case-base, learn a neural network that fills in the gap in the case-base. Or you plug it in as a plug-and-play prior, a learner network that acts as a general denoiser from any kind of distributional noise. And you plug this into a conventional reconstruction, or you can also pair this then with another neural network that takes on this a priori information. One example, and this is work that we have been doing, is the CNNet for this physics-based unrolled reconstruction. So what you see here is you have these regularizers that are learned. They are doing this image denoising task, the aliasing task, and intermittent in between of them, you have these data consistency blocks that ensures fidelity to your acquired raw case-based data, and including the coil sensitivity map, since you have multiple receiver coils for the MRI. And in this particular example, we have looked at cine data, at 3D cine data. So we needed another twist to really make the most out of the data, since we want to share as much spatial temporal information as possible. We also devised so-called 3D convolutional spatial and 1D convolutional temporal filters that are learning this spatial temporal relationship in the data. And this is learned in a supervised manner. And the results you can get out are shown here. We have two different flavors in which we can run this acquisition. Either we do a very short breath hold of 7 seconds, and this is the proposed 3D cine here in the top, or we do a free breathing acquisition of 2 minutes. In the bottom line, you see here the conventional multi-breath hold 2D cardiac cine acquisition that is usually run in a scan time of around 260 seconds with several consecutive breath holds. So you already see, like, doing this in a single breath hold of just 7 seconds, or in a completely free breathing acquisition with comparable scan time, you get very good image quality. And the main takeaway is that at the end of the day, we not only want to look at the dynamics, but also want to get out the left ventricular functional. And for this, we looked at the ejection fraction of the left ventricle, and we saw very similar values with the proposed 3D cine to the 2D cardiac cine, allowing us a very comprehensive assessment, but now with a higher 3-dimensional isotropic resolution instead of just a few slices and in even shorter scan time. In another fashion, we also have looked at super resolution coronary MRI, and this is what I've done during my time in London with the group of Claudia Prieto and René Bruttner. There we have an acquisition that is specifically targeted for high resolution coronary imaging. So we have a pseudo spiral Cartesian trajectory and embedded some motion information for respiratory motion correction and for triggered acquisition to the cardiac heartbeat, to the end systolic phase. And then we're already doing an initial reconstruction, which is this PROST algorithm. It's a denoising algorithm that already provides us with a good denoised image. So this is a starting point. Now we took a different take on it. Instead of undersampling the data, we saved an acquisition time by just acquiring a low resolutional image. So we just reduced the phase encoding directional resolutions. And for that, we have then trained a super resolution GAN network to go from this low resolutional input to the super resolutional output. And to do so, we have, in a retrospective setting, had access to the high resolutional data. We simulated this downsampling to the low resolutional data, and then we can get to the super resolutional output. And this is the generator, and you train this in an adversarial fashion together with a discriminator and together with a perceptual loss overall. This is now a prospective case where we've only acquired in different sessions the low resolutional image, and we have acquired a high resolutional image in a comparable scan session. So you can see that in this coronary reformat, the image information is quite blurry, and if you just perform a B-cubic interpolation, you still get a very blurry LAD, and it's not quite clear where structures are or if there's any stenosis. But if we go to a super resolutional reconstruction, we can get very good depiction and can even identify stenosis that are happening, but now with a way shorter acquisition time of around 50 seconds in comparison to if you would run the high resolutional scan that requires roughly around 7 minutes. So it's a tremendous saving in scan time. Again, this method was trained in a supervised fashion. So the problem is always with this that we always need access to some high resolutional or fully sampled ground truths to train our models. But in recent years, there have been also developments to looking into what can we do if we don't have access to this data and maybe only have access to undersampled data. And this is work from Mehmet Akçakarya's group, where they proposed this self-supervised reconstructional method. So thinking about, you have only an undersampled data set, you can split this data set up. I'm not going too much into details, but the main ingredients here for it, you see again, you have this unrolled reconstructional network, you have again a learnable regularizer, we have again a data consistency as before with the CNNet. But now you split up your undersampled data set into a set that is only seen by the data consistency term, and another set that is only seen by the training loss on which you apply then at the end your metrics on. So you're splitting this up, and you kind of like in a ping pong game, forcing these two components to compete with each other and to self-supervised train themselves and drive themselves to an equilibrium. And this is what they been able to achieve. And oh, sorry, all the videos are apparently not playing. But you can get first pass perfusion here very nicely with this reconstruction. And they even applied it for late gadolinium enhancement, where they also can get a very good depiction of the gadolinium enhancement in even like higher accelerated cases that has comparable image quality to a lower acceleration case. Next, I want to talk you through some of the methods on the perception side. And one major ingredient for all of these methods is that we apply some type of automated segmentation. And it can be any different types of it. And also we have worked on several different segmentational examples. So here, for example, organ segmentation of different abdominal organs in different cohorts of different sizes, or aortic segmentation, or adipose tissue segmentation, and also pairing this up then with multimodality imaging, for example, like here in the case of a PET-MR imaging, where we have been interested in automatically segmenting the lesions for it. And based on these initial assumptions, we have identified that the key to making these things work is always the data on which you can rely on and train your model. And since this is often not publicly available, we've put together here a challenge, which has been now running in 2022 and 2023, a consecutive one, in which we are also planning to continue, that looks at the lesion segmentation on multimodality data in a first stage on PET-CT data, but we're now expanding this to PET-MR data sets. And there we already see that the diversity in the data is a crucial factor to consider. And especially if we later on think really applying this into a clinical workflow, we want these methods to be robust to any out-of-domain shifts, like new scanners, different protocols, in this scenario also different tracers on which we want to apply it on, and still should work reliably, or should tell us when it fails, and if it fails or if it fails horribly, should not output any results. And that's what we are trying to achieve with this challenge, to make development in this area even possible. Another important ingredient on the post-processing side, or paired and also with the reconstruction, is the motion correction. So if we are imaging in the body trunk, we usually are faced with respiratory and cardiac motion, also peristaltic motion or bulk motion in total. And for that, also deep learning-based registration methods have been applied. Conventional registration can be quite cumbersome and can be quite computational intensive. But now with deep learning, we have new possibilities to really get to a very good flow estimation field, as shown here by the arrows overlaid on the image, that allow us to map then different respiratory states here in this example onto each other, and then make use of this multi-time information so that we can match all the respiratory states onto one motion corrected state. And we've also been working on this, but taking a different take and performing this completely in the case-based domain, with the assumption that if we want to go to highly accelerated acquisitions, so very short thresholds or very short acquisitions, our data that is coming out for a flow estimation, for motion field estimation, is always obstructed in the image domain by aliasing artifacts. And depending on our reconstruction, we can maybe get a very good reconstruction, as you've seen with the CNNet. But ideally, we will already want to incorporate into this reconstruction problem a motion estimation problem. So it's kind of like a chicken egg problem. What do you do first, motion estimation or reconstruction, or the other way around? And you're always then faced with either one being a challenge. The motion correction first means the reconstruction means the motion correction or the image registration is struggling with the undersampling artifacts, the aliasing artifacts. If it's the other way around, then the image reconstruction cannot benefit from any motion information. So that's why we said we go completely directly into the case space and we eliminate the problems of these aliasing artifacts. Need to formulate now a non-rigid registration, completely different, with the assumption that we can say any non-rigid motion is just a superposition of translational motion, and translation, the image domain, is nothing else than phase offsets in case-based. So what this network is doing is learning a filter cascade that estimates this phase offsets between the different motion states. However, you can also do this in the image domain. You can also look at networks that are a little bit more robust and capable of handling this motion information in the image. This motion in the image domain. You can even go now to incorporating this in so-called group-wise registration, where instead of looking at pairs of images where you match one motion state to the other, you have a stack of images, because here in this example for the cardiac scene, we have a whole cardiac cycle that we want to cover, and we want to have a consistent flow field over the whole cardiac cycle that deforms with the beating of the heart. So instead of just doing it always pair by pair, we throw in a whole bunch of the images from the cardiac cycle, except just for one. To this one, we want to match everything. And then we can take this on in different flavors for these networks. These are two examples we have been working on, MRAFT and GRN. And you take this information then and put it into an end-to-end network, for example, here with the motion correction. So you see already the network has to deal here with this highly undersampled images. You plug this into a motion field, you get an estimation, you plug this into a motion compensated reconstruction, you iterate over this again, and then repeat and repeat. You do this ping pong game, or alternatively, you do this all in the case-based domain, as mentioned before. But this is not the only thing that you can do with motion. You can also pair this again, not only with the reconstruction, but also then with other networks like a segmentational network. And this is an example of the work from Chen Jin, where she shared then weights between a motion estimation network and a segmentational network, so that both networks benefit from each other. And I think that's also the way we see things moving now forward, that we want to integrate more these networks to jointly work together and benefit from each other by incorporating information from the other domain. And here, this example, the segmentation marks, the clear, sharp boundaries help us really to predict where motion or contraction or motion is happening, and really helps to direct here the flow fields. And this is really beneficial, so we need to really investigate more in combining and merging this information. Just showing you an example of what this can bring then to the table for this motion compensated reconstruction here for cardiac and respiratory motion cases. If you do not include the motion information, which is shown here in the top row, even going in some cases of severe motion here with this patient with atrial fibrillation, we see for a really rather mild acceleration factor already quite significant still aliasing artifacts in the image that the reconstruction is not able to recover from. But as soon as you include then the motion information, you get to again two nice clean images. For the last step, I also want to talk you through some of the reasoning processes that are happening here in these fields, and want to show you 3 different examples for that. So on the automated quality control side, we are looking at can we get automatically a quality score for the images that are happening in real time on the scanner, or even retrospectively in a large scale cohort study. This is work by Daniel Ruckert's lab, where they look at the UK Biobank data, and they looked at the cardiac cine for the long axis and short axis acquisitions, and estimated here, was this of sufficient image quality in terms of heart coverage that is later on needed to perform a reliable left ventricular functional assessment. Is this has some interslice motion due to inconsistent breath holds? And is the contrast sufficient to run then later on an automated segmentation algorithm? If you think now of this large cohort study, it's quite tedious. What you would need to do if you need to go through these images manually and mark them all as optimal, not optimal. If you have such an automated procedure in place, that gives you already this score that shows you this was an optimal acquisition or non-optimal. And even taking this further, we can take this directly to the scanner and then get us a quality score on the scanner telling us we need to repeat the scan, or we are good to go and we can continue with our further protocol. We can also leverage this information more since now these larger epidemiological cohorts become available. We can really now think about learning more of joint embeddings, and this is work that we have been looking in. Can we combine image information and learn, or can a network learn similar to a human perception what is already embedded in the image? If we think about how we train radiologists and new clinical colleagues, we are also learning over time, like the anatomy and different things to spot. So our assumption here was that also networks should be able to learn something from the ground up if it has just been given enough samples to see something here. That's why we pulled together a lot of databases and trained a really large network here. This goes already into the direction of kind of like a foundational model for this imaging scenario. The surprising fact here was for us that the network really intrinsically learns some features. For example, it can automatically separate between the genders. So the features that are learned embedded, we haven't controlled anything. We haven't told the network anything about what is going to happen here. We just threw images at it and trained it in a contrastive fashion. And just by that, we were able to separate gender, and we also were able to separate or saw directional separation for body weight in the examples. For example, here, more lean subjects are here on the left-hand side and more obese subjects here on the right-hand side. So that's very promising for us, because that really can help us now to embed or to really guide then these training procedures to a specific target, and also use this a priori information and integrate this into other tasks. If we already have learned such a rich embedding, this could also benefit other networks. But if we do these kind of things, we always need to be cautious because we can easily being confounded by these works. And this is work that we have been doing also. And this is already out now. Sorry, I haven't updated this. It's an IEEE Access if you want to have a look at it. So the assumption here is that if we have some patient coming in, we predict from their imaging data, this is a disease, yes or no, for example. So we could be there could be common causes that are influencing our imaging and our disease. This could be, for example, here, age and sex. But there could be also a confounding variable that we do not know, and that is actually driving us with the decision to being, is this a disease, yes or no? So what we want to do, we want to disentangle this from the confounding part and find some way of training it that we are only estimating our task at hand and cannot be fooled by this confounding, which would be for a network a shortcut in the whole imaging procedure to do a reconstruction, to come to a conclusion. So overall, what we found out here, networks that are confounded, they impose a certain structure in here. So we found a shortcut over a simpler task, or the network found a shortcut over a simpler task to solve instead of actually looking at the pathology at hand and identifying this. So with this training procedure, which is minimizing the mutual information between these two joint embeddings, you get no longer a distinction with your confounding. So you always need to think about now, where do you trade off your cards and what are the causal factors at the end where we really want to derive in our decisions from. So in the end, wanna wrap this up with that there are still a lot of challenges ahead of us if we think about machine learning in MRI in general. They are very application specific often and tailored solutions at the moment still available, but we see more of these methods that are combining different aspects of reconstruction with segmentation, or going over several of these processing steps together that are really making a difference. We get so far only very limited feedback, but back from all these networks back to our clinicians and also back to our technicians who are running all the scans. So that really definitively needs to be improved. And reliability and generalizability is still, for some of the methods, questionable because they are highly tailored towards specific application, specific solutions. Also now the first vendor-based solutions and products that are coming out, they're heavily tailored towards a very specific target, which is not necessarily bad in the beginning, but we need to also educate then the users who are using it, that they're using it in an appropriate fashion. Otherwise, we will always see this domain shift happening, and this will be a very common case, and it can be an easy misconception that then a network should be working in this scenario because you deem it to be very close to it, or because it was also not communicated well in which setting it should operate, in which setting it was trained on. Sometimes we even don't have the knowledge about the training cohorts, about any information, how the architecture is and everything. So we can't even deduce from that where it should be going. But we always have these shifts in terms of like scarcity of the data, population shifts, disease prevalence shifts, or maybe we have selected just a subcohort on which we have trained, just looked at a certain phenotype, just looked at a certain population and so on in training. If this information is not known, you apply to something different. That's where the problems that happen. And that's where we really need to invest more time in the future for addressing these domain shifts. So I guess there will be a change in paradigm where we are coming from a combination, or where we come to a combination of these multiple processing steps integrated into one, and where we see a better integration, hopefully into the clinical workflows with more immediate feedback. So this brings me to the end. So we have primarily seen that in the past, we have been working on more, let's say, low-dimensional machine learning, very application-specific, tailored solutions. We're now reaching towards more higher dimensional processing with also better compute capability that is available, and we are merging solutions into these joint applications. In the future, hopefully, we will come then to a more multi-purpose and generalized machine learning that really allows us now the full integration into the workflow. And also, if you think back to the first slide, we still have other sites where we need to talk about the scheduling and also about the whole procedural workflow of a patient that could also be then integrated into the steps and really be improved. And that's hopefully where we'll see this more leaning towards in the future. And with this, I would like to thank you very much for your attention, and I'm happy to take on any questions. And thanks to all the colleagues who also contributed slides here.
So thank you very much, Thomas. This was a fantastic overview, really nice. You selected one of the most challenging modalities. I would say MRI is difficult in many aspects, and I like the approach you are proposing. The talk is now open to questions from the public, but before someone steps in, I have 2 or 3 questions I really want to ask you. I think for me, the part of the motion correction or the motion detection and correction is really fascinating, because this is one of the big problems you have in the workflow. So you have an expansive and slow modality, and and you ask the patient to collaborate into a narrow space, and then at the end of this 30, 40 minutes, you get moved images which have good diagnostic quality. This is really a disaster, actually. And before your talk, I never understood why there were so many attempts in doing the case-based motion correction or the image-based motion correction. But I think, if I understood correctly, please correct me if I'm wrong, the idea of the case-based motion correction is that you can prevent or reduce the long acquisition time. So you want to detect it early and then use it, correct it, and use it to save time. Is that correct?
Exactly. So at the end, we want to come to more shortened and comprehensive protocols. Also, we have done a lot of studies on looking into the comparison of deep learning accelerated sequences now with conventional sequences. And our colleagues found very good agreement and very good image quality now with these deep learning sequences. So they are already heavily undersampled. So in this scenario, then we are faced with this chicken egg problem. If we have motion in there, so rather detect it early and being able to interact early is of great desire. And we are now working towards integration of this into the scanner, so that we can really early on detect if motion is happening and then counteract this by adapting the sequence, or by switching on then to a different reconstruction that incorporates then the motion correction as well.
The idea is not the one of, I don't know, alerting the user that there is the need to reposition the patient or to adapt to the trigger or something like that?
Yes, that is also depending on the sequence, since we have there always a multitude of possible sequences at MRI. That is also an option that we are considering. That you just get an immediate feedback to the operator, something is wrong. But ideally, we also want to take away this burden from the operator and just switch automatically to a more robust solution that you do not need at the end of the day repeat the scan or have then a motion affected scan in your whole protocol, but automatically maybe extend for, let's say, for the example, we have one motion corrupted slice in a single breath hold because it was not very compliant with the breath hold. Then we automatically detect it and we automatically repeat it. So it's just, instead of like having 10 breath holds, you suddenly have 11 breath holds in the whole scan, but then you get a whole stack of nice clean images. So that's where we are driving it.
Very nice. I think that the burden is that you need to work closely with the manufacturer of the MRI device, because this is in the black box of the device, I think. I have a last question before the others can ask them. Do you see, in terms of performances for the motion correction, a difference if the motion has a regular pattern like breathing or cardiac motion, or if the motion is originated by an abrupt movement of the patient, for example?
Again, depends on the sequence that we are looking at. For these examples that I've shown you, they are always assuming some periodicity in the motion. But if we have now the possibility to really go to a very highly undersampled scan and estimating motion from this highly undersampled scan, we are getting again more towards being able to detect also this abrupt motion. And we see that patients in longer scans, they tend not to lie still. They are also moving a lot. So we also get this very bulk motion, or patients are falling asleep during a scan. So you also get a drift in the liver position. So these are all these facets. If you assume then some periodicity in your scan and you're regrouping, rebinning then the data, you're always faced then with these problems, and you get then a little bit of blurring at the end, even though that you did motion correction. So you always need to incorporate then this, and that's why it's so helpful to have the highly time resolved motion field estimation that could really counteract then these problems.
Thank you very much. Other questions from the audience?
I would have a quick question. Hi, Thomas. This is Alex here. Maybe I missed it more on a general level, but maybe it was said and I missed it. I'm sorry if this is the case. How robust do you think, or do you estimate, are those algorithms in different settings, different scanners, different vendors, different slice thicknesses, and so on, all those different variables you have in this very variant environment of MRI, of course.
Yeah.
Did you test that, or do you have an estimate there, or is this really on one dedicated data set where it works at the moment?
Again, this really depends on the algorithm that we are talking about. Just giving you a few examples to show you the scale here. So we have looked at different deep learning sequences, for example. We do not know on which they were actually trained, but they are targeted towards prostate and abdominal imaging. And brain imaging, and we have also taken them the one that were only trained on abdominal imaging to the neuro cases and the other way around, and they work reliably well for the reconstruction. So in this regard, this domain shift is okay, but taking this to a different vendor already induces more problems. Going too far off with the expected signal to noise ratio, contrast to noise ratio in the images, you're getting a little bit of bias and or blurring then at the end of the images, which the network cannot cover. So to a certain extent, they are generalizable in this regard, but not to all of the domain shifts. And that's where we're currently investigating if towards different pathologies, everything is still in the green and we're not missing any pathologies, for example. On the other scale, for the lesion segmentation challenge, we had in the first round a very fixed cohort where we had just data acquired on our side here in Tübingen, in our institution, where we have one dedicated scanner. And then we have in the test set had colleagues from Munich who are also co-organizers of the challenge. They are operating with a different vendor, and they have provided test data. And there we already seen that performance drop for a lot of algorithms. That's why we have pushed this year for 2023 the challenge towards more this generalizability aspect. Really included a lot of out-of-domain data that was not included in the training cohort. It consisted of different tracers, different scanners, and different pathologies. And the performance before the average dice was around 0.7 to 0.8. This dropped now dramatically down to 0.3 to 0.4 for the best performing solution.
Okay.
So we still really see that there is a lot of things to still consider when we go into this domain shifts. And we really need to target in each specific application and algorithm. Again, some tend to be more robust, some are not.
Okay, very, very interesting, and really congratulations on the great work. Maybe one additional question on that. When you talk about the robustness, do you see big differences if you apply your algorithms more, if you use the technique more on a case-based level or on the image level? I would expect the robustness is a little bit probably higher when you apply it in the case base, but yeah.
No, that's a very good question. This has been driving us now the last few years Should we operate in image domain or should we operate in case-based domain if we have now the full power? And my takeaway as of today is we should be working in the case-based domain as we are not forced with all the problems that we are buying in if we first go to the image domain. But at the end of the day, it will most likely be a combination of both. Since there's still a lot of features and information in the image domain that we do not want to lose, we have now an integration of both methods where we're working in parallel on image and case-based domain and then share information between these two different networks, and our combination of reconstruction, motion correction, and both being run at the same time on image and case-based domain and then sharing information between them. So it's getting quite elaborate. That's why you also need to think about what information is then flowing in which direction, and are you then actually solving the task at hand, or are you just creating a very powerful network that somehow learns shortcuts that you haven't thought of?
Yeah. No, I see. No, very, very interesting reading. Again, congratulations on the great work. Thank you for the great talk also.
Thank you.
Thank you very much. I think we are now running out of time. I would like to thank you again, Thomas, for this great presentation and for your time. For the attendees, if you want to receive a digital copy of the certificate of attendancy and the credits for the teaching, please enter your email contact into the chat. Catherine, something more from your side?
Nothing else from my side, but just to add, of course, at the end of the seminar series, the YouTube videos of the whole seminar series will be available on the USC YouTube channel. That's it.
Thank you very much. Thank you everyone for attending and all the speakers. It was a fantastic seminar also this year, and we take the opportunity with Catherine, Alex, and Davide Chester to wishing you a Merry Christmas and a great start in 2024. Thank you very much.